السلام عليكم ورحمة الله وبركاته. يسعد صباحكم. اليوم حنكمل. So today we'll continue section 17.2. But before قبل هيك بدي أذكركم section 17.1 إنكم تحلوا solved example plus suggested examples or suggested problems بنهاية section 17.1 واللي هم موجودين على المودل في folder. بتقدر تدخل عليه وتشوف suggested problems. So please remember that every time once we finished a certain section, you must go to the textbook, solve the solved example, and then train yourself on the suggested problems. Okay. So today we'll start with section 17.2. Last time we learned how to find out the mass moment of inertia I. Today we'll continue talking about planar kinetics equations of motion. Okay, so actually once we heard that we have a planar, that means we have 2D xy, for example. Okay, if we are using this coordinate system, so planar means 2D. Okay, kinetic equation of motion, actually we have two or three equations. Two of them is related to translation. بدي أسبق الحكي عن هذا السكشن وأعرف لكم إياهم من العنوان. Okay. إحنا حنجيهم in details. Okay. So kinetic equation, we have summation of force in x-axis equal to mass multiplied by acceleration, and the x-axis, same equation, we have it in the other direction. Okay, AY, and then summation of moment about centroid or any other point, and this is equal, we'll see this value, what will be the answer of it. Okay, so those are the equation of motion or kinetic equation of motion. Okay, kinetic equation, anything we said earlier, kinematic means distance, displacement, velocity, acceleration, anything related to kinetics, that means we'll start dealing with force. So the objective for this section 17.2, is to apply three equations of motion. So those are the equation of motions. The first two equations related to translation, and the third one, as you can tell, this is moment. This is related to rotation. Okay. So we have a three equation of motion for a rigid body in a planar motion. The second objective is to analyze problems involving only translational motion, and this is section 17.2. Why we demonstrate two sections in one time? Because they are connected on the textbook, so there is no specific problems for this section. They are grouping together in the book. Okay, so those are two sections gathered together in your textbook. So in this section 17.2, this is general, talks about the principle of kinetic equation of motion, but this section talked about a specific problem which is related to translational. Translational, as you remember from chapter 12, we have rectilinear, translational, and we have, ask yourself, correct, we have curvilinear, translational. Remember? Okay. Application, let me read this application for you. Here we have a boat. This is boat. Okay. And this is a trailer. And we have a tractor. Okay. So the boat and trailer undergo rectilinear motion. You can see that the motion of this system is horizontal, or we can say rectilinear, straight line motion. Okay, translation. In order to find out reaction at the trailer wheels, so here we have wheel number 1, we have reaction, and here we have another reaction. Okay, so if we wish to find out those reactions at the trailer wheels and the acceleration of the boat, maybe here we have the centroid, so the centroid moves or accelerate in horizontal direction only. We don't have acceleration in another direction. Okay, so we need to find out reactions, as well as we need to find out the acceleration of the boat. Most of the problem in this chapter asks us to do this. Find out reaction, find out acceleration. Okay, we need first, so the steps of solving, we need first to draw the free body diagram, and we need to draw the kinetic diagram. دائما الأسئلة هتيجي تسألنا أسئلة related ل forces, reactions, moments, acceleration. دائما أول step we must draw free body diagram and then draw the kinetic diagram for the boat and trailer. Let's see. So this diagram here represent free body diagram. Okay, and this diagram here represents kinetic diagram. What do we have in free body diagram? All forces, all moments, all reactions. So here we have normal force or normal reaction at point B, this wheel, per wheel, and here we have another reaction on the front wheel. Okay, we have tension from the joint here between the tractor and the boat, and we have of course weight of the boat due to mass. This is weight equal to mass multiplied by g. By drawing those forces, we could draw free body diagram. Now the kinetic diagram, what do we have? We have acceleration on the centroid directed toward horizontal only, directed toward x-axis. Okay, because the system moves rectilinear. Okay, remember this is rectilinear motion. Okay. Okay. Now the question is, once we have one unknown, two, and we have three unknowns. So we have three unknowns. So the question is, how many equations of motion do we need to solve this problem? What are they? So I guess you can answer this question now easily, since you know that we have three equations of motion, or three kinetic equation of motion. Okay, 1, 2, 3. We have three equations, we have three unknown, so we can solve the unknown easily. Here we have another question. This is the movement of the box is translational or what? Is this translational? Yes. Is it this is translational? Is it rectilinear? No, it is curvilinear. But again, it is translational. Okay, it is curvilinear translation motion. Okay, because we have only this angle, and box will not rotate, it will translate. It's not translate in straight line, it is translate in curvilinear line. Okay, let's start with the principles. So we will limit, based on this topic, the name of this topic, the title, we will limit our study to planar kinetics. Planar means 2D. To rigid bodies, of course. We finished talking about particle in chapter 12. The remaining of the chapters talk about rigid bodies that are symmetric with respect to a fixed reference plane. So we'll deal with fixed reference plane. As discussed in chapter 16, because this section, as I said before, that deals with general case. What do you mean by general case? The motion, it could be translation, okay, it could be rotation, it could be general plane motion, okay. So here we'll demonstrate the kinetic equation of motion for the three types of motion that we learned before: translational, rotational, general plane motion. So as discussed in chapter 16, when a body is subjected to general plane motion, so for example, this is one type of motion, so it undergoes combination of translation and rotation. So in this type of motion, general plane motion, we'll use the three types of equations, okay, which is summation of force about x, summation of force about y, okay, and the rotation. So first step, a coordinate system with its original on arbitrary at an arbitrary point B is established. So here we have a rigid body. It's colored blue, and this is arbitrary point, not necessarily the centroid. So the centroid is located here. So a coordinate system is fixed on this point. So here we have x-axis, and here we have y-axis. Okay. Then after establishing the coordinate system, we'll draw what? We'll draw the free body diagram. So first step, start with establishing the coordinate system. Then draw the free body diagram and the kinetic diagram. So those are the most important steps. Kinetic. Okay. So what do we have in free body diagram? Every external source and external moments, reactions, weight. Okay. So here we have external forces, as you can see. Okay. Here we have external moment. Here we have the weight of the rigid body. Okay, etc. So those are related to free body diagram. Now kinetic diagram represent the movement of the rigid body. Okay, so this rigid body could be rotate. This is kinetic. Okay, it could be translate. Okay, we'll see in the coming slide. But note that the xy axis should not rotate and can either be fixed or translate with a constant velocity. So rotation is not allowed for the coordinate system. So it could be fixed or it could be translate, as we did earlier. Now, the equation of motion, as I mentioned earlier, that we have three equations. Two equations. Let me use another color. The first two equations represent the translation. Okay, and the third one represent the rotation. Okay, so first two equations, this is translation in x-axis, this is translation in y-axis, and this is rotation about centroid. So let's start first with the translational motion. If a body undergoes translational motion, the equation of motion is summation of force equal mass multiplied by acceleration. And notice that this force is vector, bold, and this one also vector. Okay. This can also be written in scalar forms as summation of force in x-axis equal mass multiplied by acceleration in x-axis, and this is summation of force in y equal to mass multiplied by acceleration of the centroid in the y-axis. Okay, so now if the body undergoes certain type of motion, it could be rotation, translation, general plane motion, we'll see. Do we have summation of force in x-axis? If yes, we'll write this one. We'll see the summation of force in y-axis, and if we have acceleration in y-axis, we'll write this term. Otherwise, we'll write 0. For example, the boat here, the boat in this example, we have summation of force in x-axis equal to m multiplied by agx, but if we go to the other equation or translational equation, summation of force in y equal to 0. القارب مش راح يطير، فقط بتحرك في الاكس axis. Okay, so we don't have another component here of acceleration in y axis. So this component equal to 0. Okay, so this is why we call this section as general section, because we are demonstrating the three equations, the three kinetic equation of motion. Okay, so yes, we have summation of force in x-axis, summation of force in y-axis. So here in this diagram, you can see that we are combined the free body diagram along with the kinetic diagram. Okay, free body diagram represent the external forces and moments, and also weight in black color. Okay, the kinetic diagram represent the acceleration. Okay, mass multiplied by acceleration in x-axis and in y-axis. Now, the third equation is the rotational motion equation. Okay, we need to determine the effect. We need to determine the effects caused by the moments of an external force system. So let's see the following equation. The moment about point B, arbitrary point, so summation of moment around point B equal summation of moment around point B for kinetic. So the first part of this equation represent summation of moment around B for whom? For external force and external moment, or for free body diagram, where free body diagram including external forces, external moments, and weights. Okay, now the second part is including the acceleration. You can tell that this acceleration, it could be in x axis or it could be in y axis because it's written in bold, and it could be due to rotation, angular rotation. Okay, and here it comes the importance of section 17.1, mass moment of inertia. Okay, so this part related to kinetic diagram. So here is the importance of drawing free body diagram and kinetic diagram for certain problem. Okay, so this K here represent the kinetic effect. Once we draw, this is free body diagram, and here is the kinetic diagram. Okay, so in the first part of this equation, this is related to free body diagram. This part of equation represent, or we can substitute instead of it the kinetic diagram. So here we have mass multiplied by acceleration at the centroid, which is far away from point B. So we must, in order to calculate for the moment, we must multiply this acceleration by the arm of moment. Arm of moment is this distance. Okay, here the same. This acceleration, mass multiplied by acceleration, this is what? This is force in Newton, correct? So this mass multiplied by acceleration for perpendicular distance, which is y. Okay. Now, I multiplied by alpha, this is angular momentum. Okay. Where r in this equation, r cross product, this is very important. Okay. Where r is a vector in x direction and y direction. So if we multiply it, we'll have this component multiplied by y, and here we have this component multiplied by this distance. Okay, perpendicular distance from point B. Now the summation of mass about B is the resultant momentum. So the first part. So the first part here in this equation is the resultant momentum about B due to all external forces, like this force, like moment, okay, or weight. Okay. Now the second term of this equation is related to kinetic momentum about point B, which is related to acceleration or angular acceleration. Clear? Okay. Now, keep in mind that this equation, okay, let me erase everything. Keep in mind that this equation is taken about point B. Now, if we take this equation, same equation, but now not about B, about G, what will be the difference? What do you think? Is there any difference? Because this equation about B. Now, if I wish to write it or take the moment about G, this term will go to 0. Why? Because now point G, we have only one term, which is the angular acceleration that create moment about G. Acceleration in y-axis, acceleration in x-axis passing through point G. So there is no arm that create moment. Okay, so this is equal to Ig multiplied by alpha. Okay, so if I take it about point B, yes, we have moment due to acceleration and we have moment due to angular acceleration. If I take it about centroid, then we have moment only due to angular acceleration. Okay, why we don't have moment due to MAG, cross product R, of course, because there is no R here. R passing through G. Because always, once we draw the acceleration, we started from point G. We start from the centroid. So here is the question. Here is the answer. If point B, we talked in the earlier slide, coincides with the mass center G, إذا كانت النقطة B والنقطة G هما نفس النقطة, this equation reduced to the scalar equation, summation of moment due to external force, external moment, equal to only angular acceleration. Okay. Thus, the three independent scalar equations of motion may be used to describe the general plane motion of a rigid body. That this equation. Equation 1, summation of moment of force about x, summation of force about y, and summation of moment. Either we take it about the centroid, or the third equation will be summation of moment about any other point except the centroid. So either this equation or this equation in order to have three equations. Okay? So this is section 17.2. Section 17.2 talks about the general kinetic equation of motion. Summation of force x, summation of force y, summation of moment about the centroid or any other point. Okay? Now we'll see in the coming sections that they are dealing with the three types of motion. For example, section 17.3 talks about the translation. Translation, it could be rectilinear, okay, or it could be curvilinear. And we'll see the effect of this motion, this type of motion, on the kinetic equation of motion. Now, when a rigid body undergoes only translational, all the particles of the body have the same acceleration. Okay, so I can write AG equal A and alpha equal to 0. Why alpha equal to 0? Because there is no rotation. Okay, and we prove this concept before. Remember? Can you remember where we introduced before? Do you remember this slide from chapter 16, section 16.2, when we start talking about the first type of motion, translational? Okay, we said that this body moves from one point to another. So if I want to use the relative equation of motion, I can write it like this. Now if we take the derivative, we said that this term, the relative, will equal to 0. Why? Because it remains constant. The distance between any 2 points on a rigid body remain constant. So we can say that velocity of point A equal velocity of point A at the same rigid body, and we can say that acceleration remain constant. So this sentence coming from section 16.2. Okay, so acceleration remain constant during translation, and since we have translation, that means we have no rotation. So alpha equal to 0. So what is the effect of this fact on the three equation of motion? Anybody can tell? So the equation of translation remain as is. Okay. And the only change is with this equation. Summation of moment around the centroid is equal to 0. Why equal to 0? Because we don't have any rotation. Okay. So if I go back to the previous equation, this one, this one. So here is the general equation about centroid. Okay. If we have translation, this term is equal to 0. Note that this is about centroid. Note that if it makes the problem easier, the moment equation can be applied about any other point instead of the mass center, instead of the centroid. For example, we can take it about A, sorry. So if we take it about A, and remember that first of all we draw the free body diagram, and then we draw the kinetic diagram. Okay. Now, free body diagram, you can use those forces in this equation because those forces can be converted to x and y. It depends on the coordinate system we choose. This is x, and here we have y. Okay, and summation of moment about b coming inside this term. Okay, and here kinetic we have, because this is translation. Okay, translate. See here, this is translation rectilinear, moving this body moving in this direction. Okay, then the acceleration is coming through this centroid. Then we write here 0 because the acceleration coming through this point, and the angular acceleration equal to 0. Okay, now if we take the summation of moment about any other point, for example A, then this acceleration multiplied by mass, which is force, far away from A with a perpendicular distance equal to D. Then if we take the summation of moment about A, this term will not equal to 0. It will equal to force due to acceleration. This is force, mass multiplied by acceleration, multiplied by D. We said earlier that this term referred to external force, free body diagram, and this term related to kinetic. Okay, this is equal summation of moment kinetic about A. In this scenario, we have only the acceleration. We don't have angular. Why? Because this is translation problem. Now, is it necessary to use only xy? No. We can use another coordinate when, especially when the rigid body is subjected to curvilinear. Sometimes it is easier to use NT coordinate system when we have curvilinear translation. Okay, here we have curvilinear translation. Then apply the equation of motion for NT. So we have first equation about normal direction. Okay, and this is equal mg in n direction. Okay, summation of force in t direction. Okay, and then the third equation, either this one or this one. So if we take it about centroid, this is equal to 0. Okay, here is the kinetic. This is the free body diagram. Okay, and this is the kinetic diagram. Okay, the kinetic diagram, on this diagram we draw the acceleration. Okay, so this is curvilinear translation. So we have mg in t direction and we have mg in the n direction. Okay, now if we take summation of moment about g, both of those acceleration passing through point g, so it is equal to 0. If we take it about any other point, so we'll see the distance between G and B regarding to mg in normal direction. So this force far away from point B, distance of h. So here we can see h multiplied by mg n. And here the tangential acceleration far away, a distance equal to E, perpendicular distance for sure. Okay, so here we can see E multiplied by tangential acceleration. Procedure for analysis. First step, establish coordinate system, either x, y, or nt, depends whether we have translational rectilinear or translational curvilinear. Okay, then second step, draw free body diagram and then kinetic diagram. Okay, on this diagram showing all external forces, moments, okay, and the inertia forces, okay, and couples. Identify the unknowns. Apply the three equations of motion. Either we used XY coordinate system, okay, or we use NT. It depends on the question. Okay. The third equation, it could be moment around centroid or any other point. Okay, either in XY system or NT system. Remember, friction force always act on the body opposing the motion of the body. And here we come to the first example. I will explain this example in the coming lecture. Thank you for listening and see you soon.